Hey guys, my name is Will Buchanan, and I submitted my lab on Sunday, but unfortunately learned that the audio did not work. So here's my retake, and hopefully you guys see this. So this is my Physics 2211 Lab 1. So for the introduction, in this lab, I tracked a real object rolling along a smooth surface, which in this case was a expo marker on a table. And then I used a computer program to model a similar object over the same amount of time with a very close initial velocity. And my prediction is that the marker and the modeled object will initially have similar speeds, but I believe that the marker will decline in velocity over time due to the rolling friction with the table. In the results, I compared the distance over time between the actual object and the computer programmed model. So here's the code used to model the object that is similar to the marker. And most of the code was already given, but the two big things were that I set the while loop to be 1.59 seconds because that's how long I recorded the marker for. And I adjusted the velocity to 0.00180 to match that of the marker. And those were the two big main changes I made to the code. And then here we see the tracker program I used to follow and record the velocity of the marker because it'd be very difficult to get a precise velocity by just clicking frame by frame. But fortunately, this program does it for you. And you can see here in each frame, it captures the initial distance or the total distance traveled over a certain amount of time, and we'll graph them out for you here. And what we really want to look at is the X direction because it doesn't really change at all in the Y direction. It's a pretty straight line. But here in the X direction, we see a pretty constant velocity, but we do notice a bit of a flattening out or a slope decrease right here. And that is due to some rolling friction the marker starts to experience right around this area of the table. So next we have the velocity of the marker in blue and the velocity of the computer modeled object over time. And of course, with the computer modeled object, it has a constant velocity throughout. So we see just a perfect slope right here. And this perfectly flat slope displays a constant velocity because in the y-axis, it's total distance covered. And in the x-axis, it's time covered. So constant distance over time is going to have a perfect velocity. Whereas the marker, we see it's pretty close, but not perfect. And that is because the marker initially has a very similar velocity for the first second or so, but towards the end here, we see the velocity of the marker begins to decrease and begins to flatten out as the distance over time decreases. And that is because the friction the marker experiences slows it down from the constant velocity it was at for the first second or so. And one question we were asked is, what if the x-axis was flipped? And the answer is pretty simple. If we look at the graph, it would just, the slopes would be perfectly flipped. So the lines would start up here and go and work their way down to zero. And they would have a negative slope with the same value instead of the positive slopes we see here. And any imperfections in the lab. So one imperfection is that the marker did not roll perfectly straight along the table right next to the meter stick like I hoped. It kind of rolled along and then tailed off on the table a little bit, which wasn't ideal, but the results were good enough to use, so I kept it. And imperfections in general, I would just say like recording the marker and just conducting that experiment because, you know, the computer program is going to be perfect, but a recording that you did with a marker on a table could be close, but there's always going to be little things that go a little bit wrong. And then in my conclusion, I was actually pretty surprised by how close the marker was to the computer program because they had such similar velocities, like down to the second or third decimal, all the way through the first second. And I think this was achieved because I used such a short clip of the video, just like the very middle section when the marker was rolling pretty well. And I used a pretty smooth surface and a pretty smooth marker, which helped minimize the friction. And the dip at the end displayed by the marker is due to the friction, as I've already said, that experience between the marker and the table. And because the distance over time curve slopes downwards in the marker's graph, that will count as a change in velocity. And we can conclude that the net force was not zero because the marker displays deceleration or a decrease in velocity, which means there was a net force acting on the marker. The net force was not zero. And that's pretty much it. It was a pretty straightforward lab. Thanks for watching.